recording now. All right, so I'll go ahead with the introduction. Our speaker today is Arika Egan. She is a PhD candidate at UC Boulder and LASP, and she's the lead grad student on the CubeSat and has a hand in all parts of the mission, including the instrument calibration, integration and testing, development of the in-flight operations, and eventually data analysis. My favorite thing about Arika is that she plans to be a one-stop shop for running small space missions. I'm excited to see what kind of Qt holds for observations of exoplanets and maybe some of the future work that Arika plans to. So go ahead and take it away, Arika.
Great, thank you. So yeah, as introduced, my name is Arika. I'm a fifth-year grad student at the University of Colorado Boulder, and I work at the Laboratory for Atmospheric and Space Physics on the Colorado Ultraviolet Transit Experiment, which is a small satellite that is designed to observe short-period hot giant exoplanets in order to understand atmospheric inflation, escape, their composition, and other things as well. So here's an overview of what I plan to talk about today. I will give you an overview of the mission's technical details and how they were driven by the science of the field. I'll talk about the bandpass and why it was chosen. And I'll discuss the significance of the Qt mission to the dedication of its science. And then I'll tell you about how the instrument is designed and my work assessing its optical performance and our expected signal. So on the Qt project, the instrument is where I spend the majority of my time, and that's the bulk of my work. So that's what I'm really excited to talk about. And then I'll finish this seminar describing how the Qt team is getting ready for launch and how we expect to run the Qt mission once we are in orbit. And then here's some information about the logos on the header of this presentation. On the top right, you'll see the Qt mission logo, and then the logo for Cusp, which stands for the Colorado Ultraviolet Spectroscopy Program, which is a premier ultraviolet technology development research group that I'm a part of. And then there's the NASA logo, because Qt is the first grant-funded UV CubeSat for astrophysics from NASA. And then on the top left, you'll see the Laboratory for Atmospheric and Space Physics, which is a larger research institution that Cusp and Qt sit within. Okay, part one, the science drivers. So here's an overview of the important mission and technical elements of the Qt mission. Qt was proposed in 2016 and awarded in 2017, and it was designed specifically to obtain transmission spectroscopy of short period planets. It's the first dedicated UV astrophysics exoplanet mission. On the right is a CAD rendering of Qt in space, as well as a larger version of our mission logo, so you can see just how cute it is. So the Qt is a near ultraviolet spectrograph with a bandpass between 2500 and 3300 angstroms with a resolving power of about 2000. So it's a mid-resolution spectrograph. During its 8-month nominal mission lifetime, we hope to observe more than 10 targets, and all of these targets have orbital periods fewer than 6 days. And we want to get at least 10 transits for each of these targets. And then when the planet is in transit, we'll have an observing cadence of about 5-minute observations. And for each transit, we plan to observe roughly half of the orbital phase centered on the mid-transit. So all of these points have their own heft in the mission's design. So I'm going to run through them and explain their significance in a little more detail. So let's start with the bandpass. Qt's near ultraviolet bandpass will probe the middle to upper regions of these short period giant planets, usually nearing or at the exosphere of the planet. We can see the extended size and composition of the exosphere by looking at the transit light curves of specific atmospheric tracers. And you can see this on the graphic on the left, which is an illustration of the hot Jupiter HG 209458b. Far ultraviolet Hubble observations have shown extended absorption in hydrogen, lime, and alpha, as well as carbon and oxygen and silicon. And we believe that these heavier metals are trapped in a hydrodynamic outflow of gas from the planet. And then on the right, you can see another example, which is of an impressive hydrogen, lime, and alpha light curve for the hot Neptune GJ436b, where the lime and alpha transit depth is at least 50%. And you can see this contrasted with the 0.68 transit depth as seen in the optical continuum light curve, which is shown in that shaded pink bar. One thing to note on this data set is that it took 8 visits over a period of 6 years to make this extended light curve, and it's not even totally filled out yet. So these images are meant to illustrate the magnitude of the potential extended atmospheres on short period giant planets. So now let me show you a recent example of how this phenomena manifests in near ultraviolet observations. So this is a striking transmission spectra of the hot Jupiter WASP 121b. The data was taken with the STIS E230M grading, which has a resolution of 30,000, but the data was binned down to a resolution of 650, which you can see as the colored dots on this plot. The black line sitting at the bottom right here is the planet's transit depth as seen as the optical and infrared continuum. And then the red line marks the Roche lobe of the planet. So this entire region, this entire bandpass really shows significant absorption with transit depths that are really far above the optical and infrared continuum. And then shown here in particular, and this is what was pretty amazing about this observation, are the metals that have been seen in absorption above the Roche lobe, which means that they're likely escaping the planet. So you have this iron complex at 2,400, another iron complex at 2,600, and this magnesium 2 at 2,850 angstroms. And I believe that this is also one of the first examples of extended iron absorption in the upper atmosphere of an exoplanet 2, which is really cool. So by the very fact that we can see these ions that are present in the upper atmosphere, number one, we're already characterizing the composition of the atmosphere. And so we can learn something about what exists in the upper atmospheres of these giant highly irradiated planets. So then second, refractory species like iron and like magnesium, they're expected to be sequestered in the clouds in the lower atmospheres, meaning that their presence in the upper atmosphere indicates that they were freed from clouds or from condensates or something. So maybe they were photoionized, maybe they have been evaporated. So by learning about what ions, if any, reside in the upper atmosphere, we can better model how they got up there and connect models of the upper atmosphere to models of the lower atmosphere. So then lastly, one other major question that's actually, it had a paper written about it in the 2020 Decadal Survey written by Jesse Christensen, surrounds how we model clouds and hazes in an exoplanet's atmosphere. So with infrared data, and sometimes optical data, there's a lot of model degeneracy when you try to fit for clouds versus hazes in a planet's atmosphere. And so this figure comes from a paper by Goyle et al. In 2018, and it displays this degeneracy pretty clearly, especially on the left plot. So each of these different colored models are different levels of cloud and haze enhancement factors here. And so you can see that in the infrared, there's all of these models really overlap, and you don't see them start to become disentangled until you get down into the near infrared, the optical, and especially going into the UV too. And so we can use optical near UV data to help separate the degeneracy, break the degeneracy between these models. And so several studies, including Singh 2016 and Wakeford 2018, find that you can anchor near ultraviolet data to near infrared data or optical data to break the degeneracy of these models. And with exoplanets in their atmospheres, there are a lot of optical and infrared data, thanks in part to a lot of really high quality ground-based observatories. But that means that the ultraviolet is an underexplored regime because you can only do it from space. And so getting more UV observations can really enhance the infrared observations, the optical observations, as well as our understanding of exoplanet atmospheres as a whole. Okay, so that's the end of the bandpass section. So now we can talk about CUBE's dedicated mission architecture. All true ultraviolet observations come from space. And right now, the only observatory that can get transmission spectra is the Hubble Space Telescope. Near ultraviolet Hubble Space Telescope observations look like these two light curves right here. These are true transit observations for WASP 121b, the left, which was taken in February of 2017, and the right taken in April of 2017. So they're 2 months apart. Each cluster of data points on here represents a single Hubble orbit. The top plot are normalized raw data points. The middle plot is the data points with systematic trends fitted and removed and a light curve fit to the data. And then the bottom plot are the residuals between these two. And so you can see that each observation, so between the February light curve and the April light curve, there are some pretty significant differences in the systematics between these two observations. And so that's actually been quite a challenge with analyzing Hubble Space Telescope exoplanet observations, is how exactly do you remove the systematics from that? And so because of the difference of the systematics, the authors of this paper actually had to remove the 5th orbit of the February transit because the signal drift was so high and it was so different from the rest of from the signal drift in the other orbits of this observation. Now, dropping an orbit due to higher systematic trends than others in the light curve series isn't uncommon in Hubble transit observation analyses. But it is unfortunate to remove a whole orbit from these observations when Hubble time is precious and the data can reveal some really interesting phenomena. And because of this removal, we lose the ability to really constrain the out of transit baseline stellar flux. So even though we have one orbit from April, we don't have anything over here from February, and it makes it hard to make a true comparison between these two transit observations. So CUTE is going to lengthen both sides of these light curves by at least a factor of 2 or more, which will give us a really strong stellar baseline against which we can make transit measurements. And even if there's some extreme signal drift in 1 or 2 of these orbits, we're going to really go far beyond the transit ingress and egress to really capture behavior at the wings of the transit. So filling out this large stellar baseline will also allow us to characterize if there's any stellar variability that happens in this bandpass that we need to account for. And this extended observation is also really good for most of CUTE's targets because for most of CUTE's targets, there's no foreknowledge of their atmosphere's extent. Some of them have optical and infrared observations, but we really learn about the extent of the atmosphere when we get into ultraviolet observations, which most of CUTE's targets don't have. So therefore, this wide phase range will really allow us to capture the full ingress and egress of the transit. And then second, CUTE's observing strategy really wants to avoid some of the pitfalls with using the oversubscribed Hubble Space Telescope. We want to avoid large gaps in our transit light curves. We want to fill it out as much as possible in as short a time as possible, rather than the 6 years that it took for GJ436b. And in fact, I believe CUTE won't even be orbiting. It won't be in flight for 6 years. I think the maximum time we have, just due to atmospheric drag, is 3 years. So we won't even have 6 years. So we want to fill out the light curves of our targets as quickly as possible. So shown here is a simulated light curve of the hot Jupiter HD 209458 with the 100 angstrom bandpass centered at 2900 angstroms. And this is simulated using CUTE performance curves. The gray points here create a full light curve from 6 different transit visits, and each gray point is a 5-minute observing time, 5-minute exposure time. And then these red diamonds show the light curve with the data bin down to 30 minutes. And this simulation is a great example of what the CUTE team hopes to achieve with all of our targets after we launch later this year. Additionally, since all of our targets have an average orbital period of 6 days and a maximum orbital period of an average of 3 days and a maximum of 6 days, we can typically observe 3 to 5 transits per week and obtain 10 transits for 10 targets within 7 months. So if you include 1 month of commissioning after relaunch, we can complete our full science mission in just 8 months. And then, so within this 8 months, CUBE will be able to dedicate more than 1,000 orbits to studying exoplanet atmospheres in the near ultraviolet. So over the last 17 years where we've been studying exoplanet atmospheres with the Hubble Space Telescope, fewer than 100 orbits have been used to obtain NUV transit spectroscopy. So we're really talking about an order of magnitude more dedication that CUBE can do than Hubble, merely because Hubble is really oversubscribed, even though it's really good at what it does. Okay, so to sum up, the CUBE mission will be able to create totally filled out light curves over half of the planet's orbital phase, first allowing us to capture the stellar baseline, second allowing us to capture the full ingress and egress, and third accomplishing both of those for at least 10 targets in less than 1 year. So there's a real niche of science and instrumentation that CUBE is filling that's currently unfilled by any space observatory right now. Finally, data from the Hubble Space Telescope is not easy to interpret or reduce. Within the extant publications, there are some incongruent analyses of the same data set regarding the detection versus non-detection of atmospheric constituents. So 2010, cosmic origin spectrograph and UV observations of the planet WASP-12b revealed a potential early ingress, but follow-up observations in 2015 didn't show signs of this early ingress. And then another example, NUV observations of HC209458 detected neutral magnesium in transit, but a reanalysis of the same data set called that detection into question just by using a different analysis technique. And then the authors of the WASP-121b NUV observations fit 2 to the 13 different models to their data. So that's between 8,000 and 9,000 different models of different parameter combinations in order to detrend the Hubble systematics from the transit light curve. And that's crazy. Hubble has gotten a really great set of data for exoplanet science, but the instrument wasn't designed specifically for exoplanet science. So there aren't any strong on-ground or in-flight calibration of the telescope and instrument systematics. And the CUBE team is anticipating these problems, and we are addressing it in 2 main ways. So first, in 2018, the CUBE's large and international science team, pictured here, started a data challenge where 3 different teams from Colorado, Australia, and the Netherlands are given a simulated CUBE data set with unknown systematics and unknown star planet parameters. The goal for each team is to use their own modeling tools to retrieve the transit depth and the star planet radius ratio. Luca Fasati actually, and Srijith, that's Luca and that's Srijith, and they're both at Austria. They're actually the 2 that have been running this data challenge. So Srijith built a nice cute data simulator and he simulates the data, and then Luca decides on the initial star and planet parameters. So then by comparing the results from each team to what the original simulated data set is, we can identify where within these different models disagreements lie and account for them in new data challenges. So this allows us to preemptively improve retrieval fidelity among all CUBE science teams and separate the model differences from the data itself. And we are also planning on modeling the thermal and jittering effects of the spacecraft itself during the remainder of our integration and testing process, but I'll speak to that later. Okay, so to sum everything up, CUBE is designed to look at the inflated and potentially escaping atmospheres of short period exoplanets, typically the hot giant inflated ones. Hopefully CUBE data will help connect and fortify models of lower and upper atmospheres by providing constraints on the NUV slope. And then CUBE will also create full transit light curves covering half of the transit phase for 10 to 12 targets within 8 months. So now I'm going to tell you how CUBE is designed and some of the ways that we're testing its functionality. Okay, part 2, the instrument performance. Okay, so CUTE is a 6U spacecraft. The U stands for unit, and in CubeSat land, 1 unit is a 10 by 10 by 10 centimeter cube. So a 6U CubeSat means that the spacecraft body is 6 of those cubes, or it's 10 by 20 by 30 centimeters, roughly. We have 4 solar panels, which increase its largest dimension to about 90 centimeters. The telescope and the spectrograph occupy 4U of the entire spacecraft volume. And the telescope is made of a rectangular Cassegrain telescope, and there's a spectrograph hanging out on the back right there. And then there's a heat strap that's connected to the outer spacecraft wall that serves as a thermal sink to help keep our CCD cooled. And then the remainder of the 2U of the spacecraft contain our avionics modules, which includes the star tracker, sun sensors, radios, instrument electronics, reaction wheels, things like that. And the whole internals and the avionics module and the solar panels were provided by Blue Canyon Technologies, which is located in Boulder, Colorado. One of the most unique features, in my opinion, of the instrument is the rectangular primary mirror. And I think it's actually a really cool design because the rectangular mirror actually increases our throughput by more than 3 times in the CubeSat form factor than you would get with like a standard 9 centimeters circular diameter. And more collecting area is always better, especially when you're trying to observe small signals like exoplanet transits. Okay, so here is how light is going to travel through the system. On the left, these 3 images are CAD renderings of the instrument, and then on the right is a ray trace. So I'm going to walk you through all these different panels. Okay, so let's start with the top left. After reflecting off the primary and secondary mirror, on-axis light passes through this central spire, which has all these little ridged baffles on it to reduce scattered light. And then it enters the back of the spectrograph. And then once light is inside the spectrograph enclosure, it hits this 90-degree folding flat mirror before passing through the Cassegrain focus. This is right at the center of our slit, right here. And then after passing through the slit, light is reflected off of our grating. It's and diffracted, reflected and diffracted, and then sent to a final fold focusing mirror right here before landing on our detector, which you can see in the lower right, or lower left image. So the CCD is cooled by a thermal electric cooler and a stack up that's contained of several different copper parts that are then connected to the heat strap right here. And together, all 3 of these work to remove heat from the CCD that will then just be radiated off the side of the spacecraft wall. So this is what the actual telescope and instrument looks like. One of our engineers, Nick DeChico, is making some measurements of the spectrograph on the left over here. In the top is the telescope in the 4U of the spacecraft. And in this image, we were doing a fit check of the telescope inside the spacecraft chassis. And you can see that this little gap right here is actually where a radiator panel is supposed to go. And we can remove it. So as we're putting the shell onto the telescope, we can actually see what's going on. And then on the right, you can see the spacecraft in almost its entirety. It doesn't have the telescope inside, but it does have this radiator panel on the side. It doesn't have the solar panels, but it does have the 2-unit avionics module attached right here. So as I stated before, CUTE is really small. It fits in a very small package. The package is about the size of a Costco cereal box or a nice shoebox. So it requires similarly compact testing setups to test its performance. I'll be discussing 2 ways that we've assessed the instrument's optical performance. So first, we want to know what the effective area of the spacecraft is, and one element that really impacts this is the diffraction grating. And then second, we want to know what our spectral resolution is so we can see what kind of science that CUTE can do. So I'll start by describing how we measured the diffraction grating. The cube grating is really small. In this picture on the left, those are my hands holding it, and I wear size extra small gloves, so you can see how small it is. It's basically just a 3 centimeter by 3 centimeter small piece of glass. The grating is an aberration correcting diffraction grating, which means that it focuses light in addition to diffracting and reflecting it. So in order to measure this, I designed this custom setup, an illustration shown in the middle and an actual picture of it shown on the right, to measure how well this grating reflects light within our bandpass. The cube grating has a radius of curvature of about 4 centimeters. So the beam is very, very fast, and we needed to design a very close and compact setup in order to capture that very fast beam. So it can actually, all the light can be captured on a detector and it doesn't expand past the detector. And then as an aside, just because this setup is so small, and one theme that I've learned working on Qt is that having an experience on large spaceflight missions doesn't really translate to having a small spaceflight mission. The needs for a small mission versus a large mission are really, really different. And so having, instrument experience on a large mission doesn't necessarily mean that you're going to be an expert right off the bat for a small mission. So here's how well the grating reflected light. We have an overall efficiency of around 65%, which is pretty good for an optic like this. So 2 members of my research team, Amelie on the right and Jared on the bottom, helped in taking this data, as well as helping me make sure that the setup worked as we needed to and that it was repeatable and reliable. So we can fold the grating efficiency into an effective area curve, and we come out to an average of 25 centimeters squared. You can see Qt's effective area on the plot on the right in the context of some other NASA UV missions. I've run it, and these missions are on the left, and I've represented Qt as a Costco-sized Special K serial box, roughly to scale of these 2 missions. So despite its small form factor, Qt's optical performance exceeds that of the Galax NEV Grism mode, redward of 2750 angstroms. Galax has a 0.5 meter primary mirror diameter, while Qt's mirror is 20 centimeters by 8 centimeters. Qt's effective area is also on par with the Swift UVOT V Grism. And I think that's pretty impressive. So granted, these satellites are decades old and Qt is very new, but I think it's a cool demonstration of technology and mission evolution nonetheless. So next I'll show you a little bit about how we measure the telescope, as well as the spectrograph performance. Okay, so we focused and assessed the spectrograph performance in one of CU LASP's vacuum calibration facilities, which has historically been used for sounding rockets. And it's this chamber shown in the top 3 pictures right here. The chamber is about 2 feet in diameter, and there's a large collimating optic all the way in the back. You can see 2 rails that are running the bottom sides of the tank. It's called the long tank because it's very long, that historically hold sounding rockets on them. But we designed the special tip tilt mount to hold the Qt spacecraft, or the spacecraft and the instrument on it as well. And so in these 2 pictures in the center and on the right, you can see the instrument in 2 different orientations. So the top left picture shows me and a postdoc, Amelie, showing off our first installation test run of this mount in the chamber. And then Jared on the bottom is an undergraduate that worked in our lab for almost 4 years as a machinist. And he made a lot of the pieces that actually went into this mount. And he's now an aerospace graduate student. And then you'll also notice that on the rightmost picture, we mounted the telescope on its side. And we did this to make sure that the Qt secondary mirror, the central baffle spire, and the spider blades, since those are all mounted through the primary mirror, we wanted to make sure that the gravity vector acting on the spectrograph and the secondary mirror didn't have any effect on the spectrograph performance if we changed the direction of that gravity vector. So we mounted it on its side to change the gravity vector. We also, just recently in the first or second week of December, we conducted a vibration test with just the telescope and the spectrograph. And so we went to a local vibration facility. We put Qt, the telescope, inside of the chassis so 4U of the whole spacecraft, onto a vibe table, and we vibrated it in all 3 axes. And so a vibe table is essentially just a giant speaker. And so on these orientations, first we did X, and then we did Y, rotating at 90 degrees, and then they can flip the vibe table 90 degrees so you can get a vertical test as well. And the good news is that both the gravity load test and the vibration test showed no degradation in the spectrograph performance. And this means that we don't expect the launch or the shift in microgravity to have any impact on the instrument's spectral resolution. So we feel comfortable making performance estimates using the laboratory data that I was able to get from the tests I showed previously. And I will show you what these estimates look like next. Part 3. Moving to launch and beyond. So this is an actual Cube Spectra from the long tank. Here you can see the full CCD image, which is 2048 pixels wide and 515 pixels high. And the spectrum here is from a Mercury pen ray. You can see several lines that are visible by eye, which cover nearly the entire Cube bandpass. And so measuring the spot size using the full width half max at several of these lines allowed me to verify that the spectrograph was at a consistent focus throughout the bandpass. The vertical streaks that you can see here are an artifact of the CCD being read out and the shutter or the light source not being closed. We do have a shutter on the actual instrument, and so we're not going to see these streaking effects in space. So then from this data, we've learned that our flight unit has a resolution of about 2000. So using this lab data, I took some high resolution spectra of HD 209458, and I convolved it down to Cube's spectral resolution. So the gray line on this plot is the 30,000 resolution spectra, and the red is Cube for a subset of the Cube bandpass. And what this shows is that we can still isolate interesting atomic spectral features like magnesium-1 and like magnesium-2. Additionally, if you think back to that really nice colorful transmission spectra of WASP 121b, that was been down to a resolution of 650. So the CUTE team feels that this science that we're interested in is really going to be doable for CUTE. So we can see these features in the star's spectrum, but what kind of signal do we expect from a transiting planet and its atmosphere? Well, I've tried to show that here. So what I've done is I've calculated the uncertainty on the detected transit signal for several CUTE targets. And all of these in this plot right here are normalized to the specific CUTE target. The target is listed on the bottom. And the fractional planetary radius sensitivity is listed on the y-axis. And so each of these different colored dots corresponds to a different bandpass that I have integrated over for each of these CUTE targets too. So if there's anything that's at 10 to the 0, then we have an uncertainty of 1 planetary radius. So what you can see here is that for especially bright targets like Celt 9 and Celt 20, we're sensitive to less than 10% of the planet's radius. And for broadband stuff, we're nearing the 1% area as well. So we consider these estimates to be upper limits because we expect to observe approximately 10 transits for each target. And I've made this plot folding over 6 transits just as a proof of concept. But really, like, that's what this is. It's a really cool proof of concept using laboratory data that proves out CUTE's design and observing strategy. So we really think that CUTE is going to work, and it's going to do some really cool science. Okay, so now this flow chart provides a general overview of the remainder of the CUTE integration and test flow. Each colored block is a milestone on the bottom for on the way to launch, and each of the boxes above it are the constituent tasks that flow into each of these milestones. So right now we are finishing up this first milestone right here by characterizing the flight instrument and making sure that it works. Following that, we integrate the instrument into the spacecraft and we conduct a comprehensive performance test, which is where we verify all hardware and software functionality and performance. And then following that are two, my apologies. Following that are two environmental milestones. So the first is making sure that the spacecraft can survive the launch vibrational environment by conducting a spacecraft-wide vibrational test. And that will be very similar to the instrument vibrational test, but will include the solar panels and will have the 2-unit avionics module on there. And then included in the mechanical checks is an evaluation of the spacecraft jitter characteristics, which will capture on an air bearing. And then thermal vacuum is an opportunity to test as we fly and verify performance in a flight-like thermal environment. And this is also where we'll be paying particular attention to the thermal breathing modes of the instrument and spacecraft, and try to model anticipated in-flight orbital modes. And once we reach that milestone, the CUBE mission will be delivered to the launch site. Finally, we have a few undergrads working on the operations side of the CUBE mission by helping with spacecraft operations and testing. So here are two undergrads, Jared and Jared, working on one of the CUBE spacecraft testing computers. Not pictured here is Julian Lambert, who has done a lot of work on the user interface for our operations scheduler. Okay, so we've got this really nice interface that Julian is building for us that will let CUBE science team members dynamically schedule CUBE observations. There are several different tabs at the top of this GUI that flow down to an eventual plan to be sent to LASP operations. So the TLE stands for two-line element, and that is for inputting CUBE satellite vector, its orbital path. The target science priority tab lets us select which visible targets have the highest science priority, and the scheduler has an algorithm behind it that prioritizes highly interesting targets first. The downlink station tab lets us choose which ground station we want our data sent to, and we currently have two at our disposal, one at LASP and one is in Fairbanks, Alaska. The exposure information lets us set the exposure time and how many darks and biases that we want. And then the visualization, which you can see on the right middle panel on this picture, shows a representation of our plan, and it includes target overlaps that it couldn't resolve, which allows the user to fix and finalize the plan. And then finally, the whole plan, once it's approved, is exported in a document that LASP operations uses to send to the spacecraft to be executed. Okay, so finally, I wanted to give you an overview of some of the science products that we plan to have downlink. So this is a simulated 2D on-orbit spectrum of HC 209-458 that I simulated. I changed the scaling on here to really highlight that you can see the spectrum in our pixels. All of these yellow lines right here are simulated cosmic rays. So we're anticipating that we're going to see cosmic rays on our CCD, and we have a couple of plans to remove them. And so this is a raw 2D trimmed image. So you'll notice that it's just barely the spectrum that's showing, and there's some region on either side of it that is part of the dark frame. And the reason that we're trimming the spectrum is just to reduce our data downlink volume so that way we can downlink more data. We also plan to downlink master biases and master darks that are created on board, as well as a calibrated 1D spectrum with cosmic rays removed on board. And this is a totally calibrated spectrum. It's been bias subtracted, dark subtracted, cosmic rays identified and rejected. And there's going to be an associated error array to accommodate this 1D spectrum too. Okay, so these are the things that you probably want to know about the CUBE mission, as far as when it launches and what's going to happen after it launches. So we launch in September 2021, this year, as a secondary payload on the NASA Landsat 9 spacecraft. And our launch date is very close to JWST's planned launch date, which means that for the CUBE mission in its primary and perhaps an extended mission, we have a lot of synergy with JWST and potentially doing some simultaneous observations with JWST. We are planning for 1 month of commissioning on board to check out operations and make sure that everything is running as we plan to before we jump into our primary science mission. We also don't have a proprietary data period. So there's going to be no more than 6 months between a data acquisition and the publication of our data to the archive so that the community at large has access to our data. CUTE data is going to be hosted on the NASA Exoplanet archive. Now, unfortunately, we don't have opportunities for guest observers. We don't have the money to provide that opportunity, but the CUTE science team is very amenable to community suggestions. And so, you know, the CUTE is a NASA funded mission, and we really want to be part of the larger exoplanet community. And so we want to work with people and provide opportunities to really expand the science of exoplanets. Okay, so finally, I'm going to end this talk on the CUTE science and engineering team. So CUTE has a very large science return anticipated, and that's partially because we have a very large and academically diverse science team to back them up. So this top picture and the people that are on the right are the CUTE science and engineering team, the majority of the science people being in this large group right here, and then the engineers shown over on the right. As well as on the lower right, you can see all the logos of the institutions that are part of the CUTE team. So that's Kevin France. He's the PI of CUTE. That's Brian Fleming. That's the instrument scientist, the instrument designer, and my advisor as well. And then that's me, and I'm holding a 3D printed 2-scale model of the telescope. Then a lot of other scientists here shown are experts in exoplanet atmospheres, either observationally or modeling. So for example, we have collaborators from Trinity College in Dublin, Ireland, the Institute for Astrophysics in Austria, the University of Arizona, the University of Toulouse, and the Southwest Research Institution as well. And then over on the right are 4 scientists and engineers, all of which are early career that are helping out with various parts of the CUTE mission. From top left and clockwise, there's Nick, who's doing a lot of the thermal work and helping out with many aspects of the mission. Dimitri, a postdoc, who's been helping out with the mission operations. There's Nico on the lower right, who's been working on the flight CCD detector. And then Stefan, our mechanical engineer. Additionally, we have had more than 5 undergraduates working on various aspects of the CUTE mission, including machining, writing that GUI, and in general, just being an extra set of hands around the lab to help us do work. Okay, so this is the last slide. To recap everything that I've said so far, the CubeSat is a 6U NeV spectrograph that will assess the upper atmospheric properties of short period exoplanets. The mission will obtain several transits of more than 10 exoplanetary systems, which will vastly increase the number of systems observed in the near ultraviolet bandpass. Its estimated resolving power of 2000 will allow us to readily isolate the spectral features of key atmospheric tracers like iron and magnesium. Then the CUTE mission is managed by the Colorado Ultraviolet Spectroscopy Program, which is a premier ultraviolet technology development research group within the Laboratory for Atmospheric and Space Physics at the University of Colorado. This program, Cusp, we host several sounding rocket programs and CubeSat programs. Another Cusp CubeSat Sprite is a far ultraviolet 12U CubeSat, which I believe is NASA's first grant-funded 12U CubeSat. And then finally, if you want to keep up with the CUTE mission, you should follow us on Twitter. We post a lot of cool CUTE updates and interesting pictures from our mission development, including things like the 4 shown in the middle of this slide. And with that, I will finish my presentation and I will take any questions. Thank you.
Thanks, Arika. That was a great talk about a really exciting mission. So I'm sure I have a couple questions, but if anybody else has questions, please go ahead and raise your hand or pop them in the chat. I'll wait a minute or two so that I don't just hog the question time and see what other folks have. So I think Elisa has a question. So go ahead, Elisa.
Hi, can you hear me okay?
Yes.
Awesome. So I had a bunch of questions, but then you answered them on the slide about James Webb synergy. So you mentioned you have potentially up to 3 years of operation. If you were funded for an extended mission, how long would that be, and what would that look like? So that could be a nice guest observer time, or perhaps joint web cute
Yeah.
calls or something.
So right now we have our target list pretty much selected for our primary mission. But like I said, like that's really amenable to what kind of new data comes out. Even between now and September, we can change our observing schedule on the fly. And so the reason that we have up to 2 to 3 years total in space is really just due to the atmospheric drag in our orbit. So we'll find out specifically all of our orbital parameters about a week after we launch. And then we'll be able to predict, okay, we have 2.5 years. And the reason we only have that lifetime is because we don't have any station keeping propulsion systems or anything on board. So we are just going to be at the hands of atmospheric drag before eventually we burn up in the atmosphere. But the next, assuming that we get the funding for an extended mission, then yeah, we are hoping to work with other community members to do simultaneous observations with whatever JWST is looking at, to do some ground-based stuff. Pascal Petit, who is one of our collaborators, has a lot of access to ground-based spectropolarimetry that we hope to do contemporaneous observations with too. So there's a lot of opportunity for the community to be involved and suggest to the CUTE team what we want to look at. We don't have the scaffolding to actually provide official guest observing time because that's not part of our mission architecture or our funding. But like I said, we're very amenable to community suggestions.
Mm-hmm. And I guess Swift observations would be cool too, if you had the wide wavelength coverage for flares or something like that.
Yep.
Okay, thank you.
I'll go ahead and ask one of my questions then. So you mentioned kind of the depth of these transits, especially if you look at some of the Lyman alpha stuff, you might end up with pretty large, relatively large relative to like visible transits. I was wondering, given the time sampling that you have here, if you have something like an asymmetric exosphere, do you have a sense of how your time sampling can provide bounds on something like that? Can you actually detect something like an asymmetric exosphere or a trailing, type of exosphere with metals or something like that?
Yeah. So that was one of the main motivations for choosing such a large orbital phase coverage for our targets, is because we've seen these extended exospheres, asymmetric light curves in the FUV. So to my knowledge, there's only been one potential early ingress asymmetric light curve, and that was maybe seen on WASP-12b, but follow-up observations didn't show that same phenomena. So in the near ultraviolet, we're really not sure what kind of asymmetries or extended exospheres that we're expecting to see. And so that's really we're hoping to, and we hope that that half orbital phase is enough to capture those phenomena if they do exist.
Awesome. I think Tom, you have your hand up if you want to go ahead.
Yeah. So when a target is, eclipsed by the Earth, do you off point and then go and do another target and then flip back to your target, or do you just wait till the target comes back into view?
Yeah, usually we'll probably wait until the target comes back into view. There are some points in our simulated observing schedule where we do go back and forth between targets throughout the duration of an orbit around Earth. But usually we plan when we're eclipsed by the Earth to start taking dark frames and Dias frames and doing calibration. And that's also the time when our onboard computer will be doing some of the onboard data reduction. And it's also potentially when we'll be doing downlink as well.
Thanks. Perfect.
I'll ask my other question then, Eric. So you had a bunch of the metals, which are super interesting for potential detection of the exosphere. And I was wondering if you're going to be looking at hydroxyl signatures too, because I know there's especially for cometary observations at 292 and 308, you have a couple of really interesting signatures. 308, 307, 3081 is pretty strong. And I imagine that'd be pretty cool to potentially see splitting of, who knows, water or something like that.
Yeah, that's absolutely on our planned list. I don't think in the current published literature that we've seen that. I'm pretty sure right now the only 3 NUV planets are WASP 12, HG 209, and WASP 121. There might be one more. I know that there are more observations in the NUV from the PanSat program, but those haven't been published yet. But yeah, so we do have our eye on that, but to my knowledge, there haven't been any other detections in the extant data sets.
Awesome. Lisa, you have a question?
Yeah, so you might have covered this, so sorry. How small of a planet can you observe? Or maybe you have constraints on like how bright a star can be?
Yeah, so we're mostly limited to about maybe the 12th magnitude. So we have to look at pretty bright stars because Cute is pretty small. And because of that, we're also looking at a different variety of planet sizes. Mostly they're pretty large, but we're also interested in looking at a variety of effective temperatures of these planets and these stars. Because one of the science drivers for us is trying to understand how the opacity, hazes, and clouds affects basically that scattering slope in the NUV. So we can constrain that scattering slope if we have an idea of is the rise in the slope and due to like absorption by metals, or is it due to clouds, the cloud properties, the aerosols, things like that. And one way you can do that is by looking at targets with different ranges of effective temperatures of the planet. And so we're also interested in looking at slightly dimmer targets, but really because Cute is so small, we do have to stick to larger and brighter close by stars. So I think the majority of our main targets are closer than 100 parsecs.
I mean, magnitude of 12 isn't bad, right? The CDPP for test targets gets pretty good around there if there's an extended mission. So maybe there'll be some kind of good targets to choose from that. But
yeah.
All right, let's see. Any other questions? If you have questions, Arika, I'm guessing people can email you at the email address that came out in the invite, or hit you up on Twitter, things like that.
Yeah, absolutely. That would be really great.
Okay, I'll wait one more minute, but well, I don't see any other questions. But thank you so much for this really interesting look at, I think, a cool, really upcoming and near-term satellite that'll be launching for exoplanets.
Yeah, thank you. And then additionally, I'll add, we have a couple of publications that detail some of the science and the testing and integration process in SPIE, which is the Society of Photo-Optical and Instrumentation Engineers. I have a couple of proceedings in there. One of our collaborators, Srijit, wrote a pretty good paper on the Cute data simulator, and that's in JADIS. And then Brian Fleming also has JADIS paper with the official instrument design and overview too. So there are quite a few papers out there that go into detail about everything else that I talked about here.
All right, awesome. If you want, we can also go ahead and email those out to those who are interested. Let's see. And if you'd like to chat with Arika, I will go ahead and leave this Zoom thing open for a couple minutes. I will probably close it somewhere around 12 because I don't know what the timing. I think it's 12:15. We have it until. But feel free to go ahead and chat with her. Otherwise, thank you for attending. And Arika, thank you again for a great talk.
Yeah, thank you everybody for coming. It was my pleasure.
Hi, Erica.